So we want to find the area of the region between these two things, the y-axis and x equals y squared minus y cubed plus 6y from y equals 0 to y equals 3. So the first thing is we could try and sketch this, but that's going to be a little difficult, perhaps as this x equals y squared minus y cubed plus 6y. But since this is currently quizzes that you can basically do whatever you want on the computer while you're taking them, you could just punch it into Desmos and see what it looks like. But we would note that if we plugged in 0 to this for y, we'd get x equals 0. So we know there's a point at the origin. And if we plugged in 3, we'd end up with 9 minus 27 plus 18. So up here somewhere at 3 for y, we also get an x value of 0. So we know that those 2 points are on there. And if we plug anything in between 0 and 3, and like plug in 1, we get 1 minus 1 plus 6, we get some positive value. So we got something, who knows what it looks like, something like this. You know, it may not look like that, but we got some function. I should probably just, we got some function over here, right? We'll just do something like that. And we could be guaranteed that it's always positive over here by looking for any y-intercepts of this. Like, where does this cross the y-axis? Well, we could factor this out to a y times a y minus y squared plus 6. And if we were to factor that further, what would we get? Take out the negative, we'd have y squared minus y minus 6. Or we'd have y minus 3 and y plus 2. So we'd see that the only x-intercepts were at 3, 0, and negative 2. So it looks something like this. And so all of the pieces between 0 and 3 are to the right here. They're in the positive part of the positive x values. So all we have to do is integrate this thing in terms of y from 0 to 3. Does that make sense to everybody? Or no? So we'll do the piece that's over here to the right of the y-axis towards the y-axis. And we're doing 0 to 3 for y values. So we got y cubed over 3 minus y to the 4th over 4 plus, what is that, 6? Well, I guess we could simplify that down. 6y squared over 2 will just be 3y squared from 0 to 3. And what does that give us? It gives us 27 over 3, which is 9, minus, what is that, 81/4 plus 27, minus all the rest of that 0. And 36, what's 36 times 4? 144, right? 144 minus 81, what's that? 63? No. Yeah. 63/4. That makes sense to everyone? Any questions on that, or did I arithmetic wrong somewhere? Hopefully not. All right. And what was a new page? What was number 6?
Wait, no, you just delete it forever.
No.
Oh, there you go. Hold on. All right, all good.
All right. Number 6, anybody? Somebody asked for number 6.
Yes.
So.
Number 6 is find the area of the region enclosed by y is equal to 8 minus y is equal to 8 minus x, and x is equal to y cubed minus 2, and x is equal to y squared minus 4.
Ah, that's a fun one. Okay. So the region enclosed by those, let's see, 8 minus x, y cubed minus 2, and y squared minus 4. Well, y squared minus 4 is just a parabola. And y cubed minus 2, no, that's not. Yeah, that's right. It should look about like that. It's just a cubic, but that's been shifted to the left. 2 is a cubic that's, in terms of, what do you call it? In terms of y. And then 8 minus x should be something like that. So my sketch isn't superb there. With any luck, you could draw something better than that. Or you could look at it in Desmos. But what we will note is we got some issues here, right? That for this region, and maybe if we sketched it into Desmos, just so we have a better, that's a basic idea of what it looks like. But let's look at it in Desmos, just to see it a little nicer. 8 minus x equals y squared minus 4, and what was it? X equals y cubed minus 2, right? Yeah, that looks about like what I did, right? We'd see that the top of this thing is sometimes this parabola, right? And the bottom of it is sometimes the parabola and sometimes the cubic. And the top of it is also sometimes the linear thing. Do y'all agree with that?
Are we just looking at the first quadrant or like the
Oh no, we're looking at the entire thing here.
entire thing? Okay.
Yeah. At least I think that's what I said. Maybe I didn't say that. I don't know. Did I say that? I don't think I specified a quadrant. So it's a little bit complicated here to sort of figure out what to do. But I think our best bet is going to be to do this in terms of y, even though there's not always one function that's to the right of another one. So the left-hand function is always the parabola. For every y value from -1 up to the top of the region 3, the function on the left is always this parabola. But the function on the right changes from being the cubic to eventually being the linear one. And so our best bet is to do this in terms of y with 2 different integrals. So one that will go from -1 to 2 of the cubic minus the parabola, and one that will go from from +2 to +3 of the linear minus the parabola. The first one will give us, and what I'm gonna do here real quick, give me 1 second here, is I'm going to just pull this into here. Can you guys still see the screen where I write and stuff, not Desmos? Okay.
Yeah.
Okay. So let's make this a little bit bigger. All right. So to start with, we're going to do this part in red. And the part in red should be an integral from -1 to +2 of the cubic in terms of y because that's the right function, minus the parabola in terms of y, because that's the leftmost function. Everybody good with that?
Wait, so you're saying the cubic is always right of the parabola? Because they look like, I don't know, it just looks like the parabola is on top of the
For
cubic.
every y value, pick any y value,
Okay,
right? Any y value from -1 up to 2. Suppose I pick this one. Which one is to the right of the other one? The cubic is to
Okay.
the right of the parabola. Pick 0. The cubic is to the right of the parabola. Pick.
okay,
And so then for the blue one, it's going to be an integral from 2 to 3 of the rightmost function, which is now this one, which is x equals 8 minus y, and then minus the parabolic function, which is minus the y squared minus 4. Everybody good with that?
so you don't need like the rest of the area or like anything else, you're just picking that one section right there? Was that specified in the question?
I guess, well, I guess that does intersect again down here, doesn't it? That
Yeah.
region's not infinite. Well, when I made this problem, I meant those. So reread that problem as the regions, the singular region that is enclosed by those three, that is including only things in the first, second, and third quadrant, but not the part that is in the fourth quadrant. I'll just say with this picture right here. That's the region I meant when I made that problem.
Okay.
Why are we splitting it into 2?
Because for some of the y values, the rightmost function is the cubic, and for some of the y values, the rightmost function is the linear one. And so we can't do the same integral for the entire thing, because it changes from which one is the rightmost function to which one is the leftmost function. Not from, well, from which one is the rightmost function at 2 to the rightmost function from 2 to 3. -1 to 2, it's the cubic. 2 to 3, it's the linear. But the leftmost function is always the parabola. Does that make sense or no?
So it's transitioning from the cubic being the leftmost or rightmost to the line being the rightmost?
Correct.
Okay.
Why wouldn't you just utilize the fact that the parabola seems like it's always on top of the cubic, and then just do a standard like top-down integral instead of a right-left?
Well, because it's not. Sometimes the parabola is on top of the parabola, and sometimes the linear piece is on top of the cubic.
The parabola is on top of the parabola? What?
Right here, like for example, at -2.5 or -3.5, where I just drew that line in the region, the parabola is above the parabola on that region. The upper part of the, at the x value of -3.5 right here, the parabola is the upper limit of the region and the lower limit of the region.
Okay.
Does that make sense?
Yeah.
And so then you just integrate this. I'm not gonna go through the steps of the simplifying and the integration, but that's the setup. The setup's the hard part, right? You know, y to the 4th over 4 minus 2y minus y cubed over 3 plus 4y. Plug in some numbers. 8y minus y squared over 2 minus y cubed over 3 plus 4y. Plug in some numbers and evaluate. Does that make sense to everybody?
Are you gonna see anything this hard on the quiz tomorrow? Like this weirdly complicated?
I didn't find this to be that weirdly complicated. Yeah, maybe. It's just a pretty straightforward area problem. Split it into 2 integrals, do it in terms of y.
Okay.
Yeah. Any other questions on anything area related?
But we'd have to solve for everywhere that they intersected if we didn't have like a picture on Desmond's, right?
You would have to, yeah. Yeah. Which, I mean, those are pretty I mean, they all came out to be nice, easy pieces, so they should have been. I wouldn't give you something where it's going to come out to be 2 plus or minus, the square root of, or the cube root of 3 or something for like a cubic or something weird like that. I'm going to give you some nice values at least. So the solving for it and setting them equal to each other should be pretty straightforward. I mean, the hardest one would be setting the cubic equal to probably the parabola, but yeah, they intersected nicely. There was a nice simple value. Any other questions on that? Let me see. Are there going to be any questions where we need to graph on our calculator? Should we always be able to do it yourself? Yeah, I mean, generally you should be able to do it yourselves. For anything on the quiz, yeah, I mean, you're going to be able to do it without a calculator for sure. Any other questions?
Can I ask a question about the volume thing? Are we still on area?
No, you can ask about the volume. That's fine.
Okay. Can you do number 3 on that?
Yes. What was number 3?
Okay, it says the base of the solid is an elliptical region given by 9x squared plus 4y squared equals 36. Cross sections perpendicular to the x-axis are isosceles right triangles with the hypotenuse in the base.
Okay, sorry. Say that again. It was
Elliptical region given
Right.
by 9x squared
9x squared.
plus 4y squared equals 36.
Okay.
And did you catch the rest, or do you want me to reread it again?
No, that's fine. Okay. Things messed up. Okay, 9x squared plus 4y squared
Equals 36.
Okay. I guess I should write that down. 9x squared plus 4y squared equals 36. Okay. And then cross sections perpendicular to the y-axis were isosceles.
Cross sections perpendicular to the x-axis are isosceles right triangles.
The hypotenuse was in the
Base.
base. Okay. So first off, we should know how to graph this. We should know what the graph of an ellipse looks like, but should be able to write that in standard form. X squared over 4 plus y squared over 9 equals 1. That's standard form, dividing by 36. Tells us we're going to go over 2 units and -2 and 3 and down 3 and have an ellipse. Okay. And we're going to have an isosceles right triangle. So those are the same, with the hypotenuse stretching across the base, right? And perpendicular to the x-axis, which tells us that our thickness should be dx. And the area of an isosceles triangle should be 1/2 the base times the height, which is just the sides there squared, 1/2 the side squared. Everybody good there so far? So
Yeah, I'm good so far.
What L is, and we need to figure out what our hypotenuse is. So our hypotenuse should be, well, from here to here is y, so from here to here should also be y. So that should be 2y. And the it's a 45, 45, 90 degree triangle. So we can figure out what L is. If you don't remember exactly, L squared should be 2y squared. L squared should be 4y squared, which should give us that L is equal, sorry, not L, L squared plus L squared should be 4y squared. So 2L squared equals 4y squared. L squared equals 2y squared, or L equals y root 2. I guess I didn't need that, right? L squared is 2y squared, so if I just plug that in there, that's just the area of that triangle should be y squared. And we then need to figure out what y squared is. So y squared should be equal to 36 minus 9x squared over 4. And so we'll just integrate from negative 2 to 2, and we'll put the 1/4 out in front. 36 minus 9x squared dx. Does that make sense or no?
Wait, where'd you get the 36 minus 9x squared over 4 from?
From my original equation?
So you, because I was good with like the special right triangles. I think I actually put like x root 2 instead of y root 2, which could have been an issue.
That's definitely an issue.
Okay. All right, that would probably be why.
Yeah.
Then
because
I
this-
just plug that in instead of changing from y to x, which would explain why yours is so different.
Yeah, I mean, if you, I don't know why you would have said that L was x root 2, because this distance is 2y. This distance
Yeah.
is not 2x. If you were doing it in this way, then the distance of that hypotenuse would be 2x, and then the sides would be, x root 2. But then you
Okay.
have to convert that to y, because then the thickness would be dy. But here, the length of the hypotenuse is in terms of y, because it's going in the y direction. But the thickness of the triangle itself is dx, so eventually it has to be converted back into terms of x. Does that make sense?
Yeah.
And that's, I'm not going to do the arithmetic on that integral, but it's, that's the hard part. The hard part is getting it set up. From there, you should be able to integrate.
Wait, so where did you get the L squared plus L squared equals 4y squared again?
Sorry, where did I get what?
Just where it equals the L squared plus L squared equals 4y squared. I'm like,
You know where I got the 2y from, or no? You good with the 2y?
yeah.
Yeah. So I mean, this is just it's a right triangle, right? And the hypotenuse is in the base, so this is just a right triangle. It says it's isosceles, so those two sides should be the same. We'll call them L and L. So L squared plus L squared equals a quantity 2y squared, right? Pythagorean theorem.
Oh, Pythagorean theorem. Okay, yeah, makes sense.
Everybody good there?
Yeah.
And I did get the answers for these up eventually last night. It was pretty late, so they're all up there now.
Just the switching of the variables, like changing from y to x and like using that's always catches me off guard and trips me up.
Yeah,
Yeah.
that's one of the things that makes these difficult. But you gotta, the more of them you practice, the better you'll get at it. So. Any other questions on any of the area or volume stuff before we move on to our new volume stuff for today? All right, we're going to take a look at this graph right here and see if we can use the graph to find the volume of a sphere with a radius of 4. This is just a semicircle with a radius of 4. We're going to use some integration to find the volume of that sphere. So take a second, think about how you might want to go about that. Any thoughts on how we might do this?
Wouldn't you have to find the area of that semicircle first?
We wouldn't necessarily need to find the area of the semicircle. What were you thinking? I mean, it's possible.
Like an equation for the area of the semicircle.
Oh, an equation. You mean an equation for the semicircle itself, or an equation for the area of it?
For the area. And no, for the circle itself.
Well, let's start with what's the equation of this semicircle, and you should know the equation of any semicircle, right? Any semicircle, if it's centered at, if it was a full circle, right, that was centered at the origin, should have an equation of y equals, if it's the top half of it, should be just the positive square root of the radius squared minus x squared, right? That's what y equals there. But how are we going to integrate to find the volume of a sphere that has a radius of 4? All right, here's how we're going to do it. Imagine we have this semicircle. Imagine we take this semicircle and we rotate it around the x-axis, okay, fully. So it's in this position where it's, up above the x-axis right now. And we push it into the screen and rotate it fully around and bring it back out of the screen, and we do a full revolution. We should be getting a sphere that has a radius of 4, shouldn't we?
Yeah.
So if I were to do that, there's my sphere, really atrociously drawn. Okay. And I were to, let's say, slice that sphere this direction, what would each cross section look like?
A circle.
Should look like a circle. In fact, it doesn't matter which way I slice it. If I slice it this way, they should look like a circle, right? If I slice it this way, it should look like a circle. But we're going to slice them vertically like this, and they should look like circles. And so that should clue us in that we could use this same method of this cross-sectional area for rotating something around the axis, because the cross sections will always be circles. Right? If I rotate something around an axis, the area of the cross sections should be pi r squared, right? Because they're circles. Everybody agree with that?
Why can't we just use why do we have to integrate? Why can't we just use 4/3 pi r cubed and just plug in 4 as our radius?
Because that's just so sad that all you can do is memorize a formula and not know where it comes from. We want to be able to know where the formulas come from, because they all come from calculus and integration. And memorizing a formula is whatever. It's boring. So this is not boring. This is learning where things come from. Maybe you're bored still, but that's fine. So the cross sections are circles and the area is pi r squared. We'd like to integrate, they have a thickness of dx, right? We'd like to integrate pi r squared from where to where? From over here at the left to over here at the right, right? -4 to 4. Because then I'd be summing together these little tiny volumes, area times thickness, of every little slice that I could make of this sphere. We'd be putting together an infinite number of these little slices. That make sense to everybody?
Yeah.
Okay. Well, what's the radius of one of those? That's the radius, right? What is that?
Why?
Y. Right? So our radius is y. And so r squared should just be y squared, which should just be 16 minus x squared. And so if we were to do pi times the integral from -4 to 4 of 16 minus x squared dx, that ought to give us the volume of this sphere, which should be pi times 16x minus x cubed over 3 from 0, not 0, from -4 to 4. Good or no?
Good.
Great. So plug it in. What do you get? You get pi times 64 minus 64 thirds minus -64 plus 64 thirds, which is what?
28 pi.
I don't think it's 28, is it? No, 64 plus 64 is already 128. All right, 128 minus 128 thirds should be 256 thirds, I think. And if I multiply that by my pi, I should get 256 pi over 3. Good or no?
Good.
And if we were to just go in and use the formula, what's the formula say? It's 4/3 pi times the radius cubed, right? Well, our radius was 4. 4 cubed is 64. 64 times 4 is 256. 256 pi over 3. Comes out exactly the same. Why is that the case? Well, suppose you have any circle of radius r. Right? And I'm just going to, well, we'll just do this. There's my semicircle. That's atrocious. Let's do this again. There's my circle with a radius of r. And we could use the same idea that y would equal the square root, just the top half of this, right? Would be y equals the square root of r squared minus x squared. And we could develop that 4/3 pi r cubed formula that we've got by doing this in a slightly simpler way. We could integrate from 0 to r. And if I integrated from 0 to r, that'd only be half of the sphere, wouldn't it? So I'd have to multiply that by 2. And then we'd also have the pi, and then we'd have the radius squared dx. Well, like we said before, our radius was y. And so our radius squared would be r squared minus x squared. And this would give us 2 pi times the integral from 0 to r of r squared minus x squared dx. Good or no? Conceptually, does that make sense?
Wait, so can you just run through that one more time? It just didn't click. Just real quick.
Yeah, so same idea. We're gonna just do this quarter of it though and rotate it around. And if I take a quarter of the circle and rotate it around, that gives me half of the sphere. So I multiply by 2. And then my area of each of these little discs that I get, each of these circles, is pi r squared, where r is the radius of that circle, and r is equal to y, which is the square root of r squared minus x squared. So r squared ought to be just r squared minus x squared.
Okay, yeah, that makes sense.
Yeah, and so, I mean, maybe we should, let's call this capital R as our radius here. I don't know, I mean, maybe that makes more sense. I don't know, we'll just leave it like that, it's fine. And so when we integrate this, what do we get? We get 2 pi And we get what's the integral of r squared in terms of x? Should be r squared x minus x cubed over 3 from 0 to r. And if we plug in r, we get r cubed minus r cubed over 3. And if we plug in 0, we get minus 0. And what do we get? We get r cubed minus r cubed over 3, which would be 2/3 r cubed, times 2 pi, which would be 4/3 pi r cubed. And that's where that formula comes from. It comes from taking a quarter of the circle, revolving it around the x-axis, and then doubling it to get the full sphere. That's how that formula was originally developed. That's why 4/3 pi r cubed works for any sphere. Right? Isn't that neat?
Sort of.
Wow. Great. Glad you're so interested in this. Anyway, that's the idea. So what we're going to do is we're going to take lots of random functions now and try to revolve them around different axes. And we should be able to find the volume of any function that we revolve around an axis pretty simply, because if we revolve it around the axis, what is each of the cross sections going to become?
Circles.
They should become circles, right? So if I take this thing and revolve it around the x-axis, I'm going to get, I don't know, whatever, like the bottom of an acorn or something. I'm going to get this three-dimensional thing that if I slice it vertically, has a thickness of dx, and the cross section of that will be a circle, and we know the area of the circle. So anytime we do this revolution, we call these solids of revolution. We can do pi times the integral of the radius squared, and then dx or dy, depending on which direction we're going. So in this case, it's dx. And so we want to integrate from 0 to 2. And all we have to do is figure out what the radius of this is. Well, what's the radius? The radius is just the y value, or in this case, root cosine x. So what's r squared?
Cosine x.
It'd just be cosine x. So this becomes pi times an integral from 0 to 2 of cosine x dx. And so that should be a formula to give me the volume of this irregularly shaped three-dimensional solid. And it should be the exact area of it, because I'm summing together an infinite number of these little slices of it, and I'm finding the volume of each one. So what's the integral of cosine?
Is the upper bound 2 or pi over 2?
Oh, sorry. Yeah, why am I writing 2? Pi over 2. Sorry. I don't know why I'm writing 2 every time. It's written right there, x equals pi over 2. Yeah, sorry. And what's the integral of cosine?
Sine.
Sine x. And we'll go from 0 to pi over 2. Make sure I actually write pi over 2 this time. Gives us pi times what's the sine of pi over 2? Yep, 1. And the sine of 0? 0. And so this figure has exactly pi cubic units of volume. Good or no? Any questions on that?
So when you first said that, the whole like, the integral from pi over 2 to 0 of r squared, was that r squared just from like the previous questions where we just decided that like any radius squared would give us the, like, well, where does the r squared come from?
Well, it's the area of a circle, right? Pi r squared is the area of a circle.
Oh, okay. Oh, okay. Yeah.
We could prove what the formula for the area of a circle is using integration if you want to, but you didn't seem real interested in the proof of the volume of a sphere, so I doubt you'll be interested in the area of a circle too. Yeah, I mean, it's pi r squared, so cross sections of circles, their area will be pi r squared. Anytime we revolve around an axis, the area of that thing will be pi r squared because that thing will be a circle.
Is that how most of these solids of revolution are going to work, where
That is
cross
how all
sections
of
are
these solids-
circles?
The cross section, there's no way to revolve something around an axis and not get a circle.
Okay. And then, so
I mean,
it's pretty much
there
gonna
are
be in
ways
this
to do it.
format.
I mean, you can get, I mean, we're going to deal with it. You can get, if it's not fully pushed up against the axis, it's like if I had, if I was trying to revolve a region that looked like this around this axis right here, right? Well, that's not going to give me a circle. It's going to give me like a washer. It's going to give me a circle with a circle cut out of it. We'll deal with that too. But I mean, effectively, that's still a circle, right? It's a circle with a circle cut out of it.
Okay, but this will be like the general format for most questions. Like the
There is
whole
no way to
R-squared.
get anything other than a circle if you revolve it around and then get cross sections of it cut perpendicularly to the way you revolved it. So we revolved around the x-axis. We cut it perpendicular to the x-axis. We will get circles, and that's how revolving things works.
Okay.
All right, so let's look at this one. Here is the function 2 plus x cosine x, and we're looking to revolve it around the x-axis on the interval -2 to 2. And we want to find the volume of that solid. So as we revolve that around the x-axis, we're going to get something. Let's see if I can draw this. It looks, I don't know, I would say it looks like a flower vase turned on its side. Yeah? Or no? Yeah. You agree, Max? It looks like a flower vase turned on its side. Yeah. You guys agree with that?
Yeah.
Yeah.
Okay. At least my child responds to me. So if I slice it vertically, what are the cross sections going to look like? They're going to be circles, aren't they? Since we revolve this around an axis. And they will have a
Yeah.
thickness of dx. So we just need to integrate from -2 to 2. The radius, and the radius on all of these should be very easy. The radius should just be the function. So it should be 2 plus x cosine x squared dx. And we have to remember to put our pi out in front because it's pi times the radius squared dx. Good or no?
Good.
And that should be the exact volume of this. Now, this is an integral that you guys do not yet have the tools to solve. So we'll have you integrate that on your graphing calculator and tell me an approximate value for that integral. You guys remember how to do your integrals on your calculator, I hope?
Yep.
Okay, so plug that in and tell me what you get. What did you guys get?
$52.429.
Anybody else agree with that?
I got the same thing.
Wonderful. Any questions or problems with the setup and any of that? We're all good? Okay. So here's what I was talking about a minute ago, where we get these cross sections that are washers. So, I mean, I think you'd all probably agree that those are pretty straightforward, hopefully, right? Revolve it around pi r squared, that's the cross section. But if we have a region that we are revolving around an axis that is not fully pushed up against what we're revolving around, right? So here's my region, and I'm revolving it around this x-axis. I'm going to get this sort of V-shaped three-dimensional object, right? And what it's going to have is it's going to have this outer ring to it with a smaller ring cut out of it. It looks sort of like a funnel, except that there's nothing cut off at the end of it, right? For stuff to funnel through. And what do the cross sections of this look like? They look like, looking straight on at them, a circle with a circle cut out of them, right? Looks like a donut, or looks like a washer, right?
That looks like a toilet seat.
Or if you ask Max, it looks like a toilet seat, according to my child, who should be in his class right now. Do you all agree that looks like a washer? You guys agree that cross section, how we got that?
Yeah. Yep. Looks like one.
Yep. Okay. So the area of that should be the outer area minus the inner area. Pi times the outer radius squared minus pi times the inner radius squared. And so this is the formula that we'll use. We'll just use our outer radius from our larger function, our inner radius from our smaller function, and then integrate across, in this case, 0 to 5. Good or no? Does that make sense?
Yeah.
Okay. So pi can be factored out, right? Pi, 0 to 5. Outer radius is what? For this one. Should be from the x-axis to the upper function, which is
X.
x. And the inner radius should be from the x-axis to the smaller function, which is x over 2. So this should be x squared minus x over 2 squared and dx. And I will caution you right now, because this is a mistake that many people make. They write this as capital R minus little r squared. Okay. Don't do that. Don't subtract the radii first and then square it. Don't do that. That is bad. That is wrong. Okay. Everybody good and not going to do that?
Wait, where'd you get the big R equals X and the little r equals X over 2? Like, where'd you get those from?
Well, this is the function y equals x. This is the function y equals x over 2. So the outer radius is the upper function. The lower or the smaller radius
Okay.
is the lower function.
Okay, cool.
And so now we'll do pi times the integral from 0 to 5. And x over 2 squared is x squared over 4. So I got 1x squared minus 1/4 x squared. So that's 3/4 x squared. And now we've got pi times, well, x cubed over 3. The 3 will cancel. So we end up with 1/4 x cubed from 0 to 5. Or 125 pi over 4 minus 0 units cubed. Good or no?
Good.
Great. All right, let's do another one. Let's find the region in the first quadrant enclosed by the y-axis and cosine and sine x. And so let's, this first region that we get, there's more regions I know that are in the first quadrant that are enclosed by them, but we're just going to take a look at this first one. We're going to revolve this around the x-axis, so we're going to get, that's mediocrely drawn, but we're going to get something that looks like this, right? With like this weird little cutout in the middle of it, right? Sort of like the last one. Good or no? I believe in the last unit, we found the area of this little region, but now we want to revolve it and find the volume. So what do we have to do that?
What were you saying? Sorry, what was the question?
What do we have to do to find this volume?
Do we have to break it up to where they intersect? Like,
Okay, we need to figure out where they intersect. So where do they intersect?
by force, right?
So that's the end of our region, right? So our integral will be from 0 to pi over 4. We need a pi out in front, and we need the radius squared, right? The outer radius squared minus the inner radius squared. Well, what's the outer radius? That's capital R. Which one is the larger function?
Cosine X.
Cosine x. And the lower region, or the lower bound of that region, is sine x. So it should be cosine squared x minus sine squared x dx. Everybody good there?
Yep.
Okay. And this should be pi. And how can I rewrite cosine squared x minus sine squared x to make that integral a lot easier to complete?
Is it -1?
Nope. So remember at the beginning of the year when I gave you this sheet of trig things that you needed to have memorized and know how to apply and use that you should have learned in previous math classes, and then you didn't do it? All of you. I remember that. This is like one of the most simple trig identities that you should have memorized last school year.
You just replace one with one minus the other.
I could, but that's not going to make it much easier to integrate.
Cosine of 2x.
Oh, good. Somebody at least went and looked up the sheet and found it, or knew it, right? Cosine of 2x is cosine squared minus sine squared. And cosine of 2x is a really simple integral, isn't it? You should be doing very simple ones like this in your head now with the u sub, hopefully. That's 1/2 sine 2x from 0 to pi over 4, which gives us pi times 1/2 of sine of pi over 2, which is what? 1/2 minus 1/2 of sine of 0, which is 0, which gives us pi over 2 units cubed. Good or no?
Yeah.
Great. You really need to know the super simple trig stuff, everyone. Like, I should ask you what's cosine squared minus sine squared, and everybody in the class should be like, oh, it's cosine 2x immediately. That's something you should have known already coming into this class. All right. We're going to stop with that one today. We're going to worry about rotating around other axes tomorrow and Thursday. Anybody have any questions on anything we've done so far today?
Why did we need to find where they intersected for this problem?
So that we knew where the end of our region was. If we'd continued on, we would have been doing more stuff. We
Oh, I see.
Yeah.
Okay, thank you.
Yep. Any other questions, anyone?